Neat little example. We'll do this one a little bit differently, though. Remember this problem we had where you throw a random dart and it lands somewhere in this circle with probability 1, and so that the density function is 0 outside the circle, but then here it's inside the circle it's uniform. Remember that? So that it's sort of equally likely to land anywhere in the circle. In fact, here's the density function we have. It's we already did this in a previous example. It's 1 over pi r squared times the indicator function that the random point is actually inside the circle. Now let's define d to be the distance that the random point is from the origin. And so let's see, how do you get that distance? Isn't it just by the Pythagorean theorem? It's going to be root x squared plus y squared, isn't it? Yeah, so maybe I want to find the expected value of d. Okay, the expected distance that this random point falls from the origin. Well, so first of all, note that this distance is going to be non-negative. So I'm going to use that. I'm going to jump off here using a different method, right? I'm going to use that useful trick. Since d is a non-negative random variable, I'm going to just say that this is the integral of the probability that d is greater than, say, a, dA. Okay. This is since d is a non-negative random variable. Okay. Now, so this is the probability that the probability that d is greater than a. This is the chance that d is less, or it's 1 minus the chance that d is less or equal to a, right? Times dA. Okay. Now, what is now? How can I write this integral? Actually, I want a just really needs to go from 0 to r, doesn't it? What is the probability that this random point falls within a units of the origin? That is, what is the probability that this random point falls within, say, a circle of radius a? Pretend this is a circle. It doesn't look like a circle, but it's a circle of radius a. Okay, the large one here is a circle of radius r, isn't it? And so it should be the case, and it is. And I'll let you figure it out if you don't believe me. But that the probability that this dart falls inside this circle is just the area of that circle divided by the area of the total. And you can figure that out. But yeah, it turns out to be this is just so this is just pi a squared over pi r squared. Or just a squared over r squared. Okay. So then this is just a squared over r squared dA. Okay. Now I'm going to continue this up here. So this is just going to be the integral. I'm going to split this now to 2 integrals from 0 to r dA, and then minus the integral from 0 to r of a squared over r squared dA. Okay, so this first integral just becomes a from 0 to r minus, let's see, 1 over r squared times a cubed over 3 from 0 to r. All right, so this is just r minus 1 over r squared times r cubed over 3, or r minus r over 3, I guess, or is that just 2/3 r? Yeah, pretty neat, huh? So note that it's so the expected distance is 2/3 r. If you look back at the picture, is that intuitive at all? I don't know. 2/3 r is here. So sort of on the average, the point is going to lie somewhere, kind of about on this circle on the average. Okay, and it makes sense that it's not half r, right? Because that there's larger areas of circles are cut out in as you approach, as you go out toward the perimeter there, right?